Hello everyone. In this lecture, we are going to explore the Ford-Fulkerson algorithm, one of the most important algorithms in network flow theory. Imagine we want to send as much information as possible from one point to another. At first, we have data packets ready to travel through a network. These packets enter a system of connected nodes. Each node can carry only a limited amount of flow, so the packets must find the best available paths from the starting point to the destination, finding the maximum possible flow through a network. Now let's move to a more concrete example. Imagine we have a small network in which one laptop acts as the source. This is where the data starts. The server acts as the destination, which is also called the sink or target. Our goal is to transfer data packets from the source to the destination through the available connections in the network. But each connection has a limited capacity, so not all packets can move freely at the same time. Now the next step is to find a path from the source to the sink. In the Ford-Fulkerson algorithm, this path is called an augmenting path. An augmenting path is any available path through the network where we can still send more flow without exceeding the capacity of its connections. As you can see, there may be more than one possible augmenting path. At each step, we select one of these paths to push the flow through the network. Suppose we select this augmenting path. Along this path, the first connection has a capacity of 10, while the next connection has a capacity of 5. Although one part of the path can carry 10 units of flow, the whole path is limited by its smallest capacity. This smallest capacity is called the bottleneck capacity, so in this case, the bottleneck is 5. That means we are only allowed to send 5 units of flow through this augmenting path. As the data packets move through the network, they may pass through one or more intermediate nodes. A key rule in network flow is that intermediate nodes do not create or store flow. So if 5 units of flow enter a middle node, the same 5 units must leave that node and continue toward the destination. In other words, for every node except the source and the sink, the incoming flow must be equal to the outgoing flow. This is called flow conservation, and it ensures that all transmitted data keeps moving through the network until it reaches the target. After sending 5 units of flow through this augmenting path, we need to update the remaining capacities of its edges. The first edge originally had a capacity of 10. Since we have sent 5 units through it, its remaining capacity is now reduced to 5. The second edge originally had a capacity of 5. After sending 5 units through it, its remaining capacity becomes 0. This means the second edge is now saturated. A saturated edge has no remaining capacity, so we cannot send any more flow through that edge in the same direction. At this point, the network is updated and the algorithm continues by searching for another available augmenting path from the source to the sink. Now we choose another augmenting path from the source to the sink. This time, the path contains 2 edges with residual capacities of 8 and 6. To determine how much flow we can send, we calculate the bottleneck capacity. The bottleneck is the minimum residual capacity along the selected path. So between 8 and 6, the bottleneck is 6. This means we are allowed to send 6 units of flow through this augmenting path. Again, if these 6 units enter an intermediate node, the same 6 units must leave that node. This follows the flow conservation rule. After sending the flow, we update the residual capacities. The first edge decreases from 8 to 2, and the second edge decreases from 6 to 0. Because the second edge now has 0 residual capacity, it becomes saturated and cannot carry more flow in the forward direction. Next, we continue by selecting another augmenting path from the source to the sink. This time, the selected path contains 3 edges. To find how much flow can be sent through this path, we check the residual capacity of each edge along the path. Among these 3 edges, the smallest residual capacity is 5. So 5 becomes the bottleneck capacity of this augmenting path. That means we can send 5 units of flow through the entire path. As before, once the flow is pushed through the path, we update the residual capacities of all edges involved. And once again, we have another saturated edge. Each forward edge on the path loses 5 units of residual capacity. For the last step, we select another augmenting path. This path contains 3 edges with residual capacities of 2, 9, and 5. The bottleneck is the minimum of these values, which is 2. So we can push 2 units of flow through this path from the source to the target. Once again, after sending the flow, we update the residual network by reducing the forward residual capacities. If no more augmenting paths remain after this update, the algorithm stops, and the maximum flow is the total flow sent through all selected paths. At this point, even if more data packets are still waiting to be transmitted, there is no available augmenting path from the source to the sink in the residual network. This means the network cannot carry any additional flow, and the total amount of flow we have successfully sent through the network is the maximum flow. So the Ford-Fulkerson algorithm stops, and the total flow already sent through the network is the maximum flow. That completes our step-by-step explanation of the Ford-Fulkerson algorithm. Thank you for watching.